Hello students. Welcome to Varun Tutorials. In this video, we are going to learn about differential equations of first order and first degree. We will cover the definitions, types, order, degree, solutions, and the formation of a differential equation. Let us understand every concept step by step, along with formulas and examples. So let us begin. First, let us look at the definition of a differential equation. A differential equation is defined as an equation involving derivatives of one or more dependent variables with respect to one or more independent variables. Next, there are two primary types of differential equations. First, we have ordinary differential equations, and second, partial differential equations. Let us define an ordinary differential equation, or ODE. A differential equation is said to be ordinary if the derivatives in the equation are ordinary derivatives, involving only a single independent variable. The general form of an ordinary differential equation of order n is represented as a function of x, y, and its ordinary derivatives up to order n, equated to 0. Let us see some examples of ordinary differential equations. Example 1 is, the cube of dy by dx, minus the square of dy by dx, plus 7y, equals cos x. Example 2 is, d squared y by dx squared, plus 5x times the square of dy by dx, minus 6y, equals tan y. Example 3 is, the quantity, x squared plus y squared minus x, times dy, plus the quantity, y times e to the y, minus 2xy, times dx, equals 0. Example 4 is, x times the second derivative, d squared y by dx squared, equals the square root of 1 plus the square of dy by dx. Next, let us define a partial differential equation, or PDE. A differential equation is said to be partial if the derivatives in the equation refer to two or more independent variables. A classic example is the one-dimensional wave equation, where the second partial derivative of y with respect to x equals 1 over c squared times the second partial derivative of y with respect to t. Another example is the one-dimensional heat equation, where the second partial derivative of y with respect to x equals 1 over c squared times the partial derivative of y with respect to t. And we also have the two-dimensional Laplace's equation, where the sum of the second partial derivatives of u with respect to x and y equals 0. In this course, we will focus exclusively on ordinary differential equations. Now let us define the order of a differential equation. The order is defined as the order of the highest order derivative that appears in the differential equation. For example, in the equation, the quantity x squared plus 1, times dy by dx, plus 2xy equals 4x squared, the highest derivative is dy by dx, so the order is 1. In our second example, x times d squared y by dx squared, minus the quantity 2x minus 1 times dy by dx, plus the quantity x minus 1 times y, equals e to the x. The highest derivative is of order 2, so the order is 2. Next, let us understand the degree of a differential equation. The degree is the highest exponent or power of the highest order derivative occurring in it, after the differential equation has been made free from radicals and fractions. This means the equation must be expressible as a polynomial in the derivatives. Let us see an example. Y equals x times dy by dx plus the square root of 1 plus the square of dy by dx. First, we must remove the radical by rearranging and squaring. By rearranging and squaring both sides, we get the square of the quantity y minus x times dy by dx, equals 1 plus the square of dy by dx. Expanding and simplifying, we get the quantity 1 minus x squared, times the square of dy by dx, plus 2xy times dy by dx, plus the quantity 1 minus y squared, equals 0. Since the highest power of the highest order derivative is 2, the degree is 2. In another example, a times d squared y by dx squared equals the quantity, 1 plus the square of dy by dx, raised to the power of 3/2. Squaring both sides to clear the fractional exponent, we get a squared times the square of the second derivative, d squared y by dx squared, equals the quantity, 1 plus the square of dy by dx, all cubed. The highest derivative is of order 2, and its power is 2. Hence, the degree is 2. Next, what is a solution of a differential equation? A solution, or integral, is any relation between the dependent and independent variables, not containing derivatives, which satisfies the given differential equation. For example, y equals a cosine x plus b sine x is a solution of the second-order equation, d squared y by dx squared plus y equals 0, for any arbitrary constants a and b. There are three types of solutions. The first is the general solution. A solution containing a number of independent arbitrary constants equal to the order of the differential equation is called the general solution. For example, y equals c1e to the x plus c2e to the 2x is the general solution of the second-order equation, y double prime minus 3y prime plus 2y equals 0. The second is the particular solution. A solution obtained from the general solution by giving particular values to the arbitrary constants is called a particular solution. For example, y equals e to the x plus e to the 2x. The third is the singular solution. A singular solution is a solution which cannot be obtained from the general solution by any choice of the arbitrary constants. For example, y equals 0 is a singular solution of the equation, the square of y prime, minus 4y, equals 0, because it cannot be obtained from its general solution, y equals the quantity, x plus c, squared. Finally, let us understand the formation of a differential equation. Consider a relation between x and y containing n arbitrary constants, c1, c2, up to cn. By differentiating this relation n times successively, we obtain n additional equations. From these n plus 1 equations, we eliminate the arbitrary constants to get the differential equation of order n. Always remember, the number of differentiations required to form the differential equation is exactly equal to the number of arbitrary constants present in the original relation.